Okay, so finite differencing is basically taking a derivative numerically. Basically, you can use left, right, or middle. Um, and there's various equations or the one equation for each of them. Um, and yeah, you just, here we're doing middle, so just the average between them. And divide it by 2. Then you can iterate down to get the numerical solution. So yeah, just a numerical way to take a derivative. So yes, the difference between analytical and numerical differential equation is analytical is right. You're doing the math on the paper. You're solving it by hand. You'll get I would say a generic solution that you could apply for various sort of conditions. Numeric though, and you can't do that for all differential equations, right? For more complicated ones, you may not even be able to solve it at all, and you would have to use the numeric differential equation. And there you would basically you'd iterate again. You'd use Excel. Sorry for my sort of dodgy explanation, but yeah, you'd use Excel and iterate, and you'd come up with your numeric solution that way. So for Poisson flow, it's pressure-driven flow between two plates from a pressure gradient. Here's my solution here. Here's my assumptions. Okay, so here's the assumptions. These are standard assumptions for Poisson flow. Steady state Newtonian, constant density and viscosity. Those are pretty standard. Fully developed. That'll give us a boundary condition. Only flow in the x direction. So this will give us, this will allow us to cancel out these as well as these. Wide relative. Oh yeah, basically these are so much wider than the length, and that'll allow us to cancel this one out, and then this cancellation and that one come from continuity. I forgot to draw a line through there, but that's because there's no gravity in the x direction. Gravity is only downward. No slip, that's our other boundary condition. And this comes from the pressure gradient. We can make those simplifications with continuity and Navier-Stokes. We get to this. Integrate to solve it. We use our boundary conditions to solve for our c values. And then from there, we can use that to solve for the values that we were needing to solve in the homework for the analytical solutions. QET, this is basically one plate will be moving from the flow and the other one will be stationary, and there's no pressure gradient here. So that's the difference. Again, same kind of assumptions here as steady state Newtonian. Constant density and viscosity. Again, it's wide relative to the height. No slip, those are both of our boundary conditions. And there's no pressure gradient and only x-directed flow. And then there's gravity only in the z direction, right? Right, so that's all of our cancellations. Continuity, steady state, continuity. This comes from only flow in the x direction. No pressure gradient, no gravity in the x direction. Continuity, and then this is wide relative to the height. That gives us our differential equation. We solve that, use our boundary condition to solve for c, and then we use those to solve for the other values. And I guess I can walk through these real quick. Yeah, this is sort of just the definition of dq is equal to velocity dA. dA is w dy. Integrate, plug in Vx that we solve for up here, gets us that. And from here, this one's in the handout. The shear is just tau times the area, and the V average is just the volumetric flow rate over the area. And same thing for those ones up there. All right, thank you.